Look, I think we may make a start. I'll just start by some introductions. Those of you who can see the webcams, there are three grizzled-looking gentlemen on the screen. The one who's talking is me, Andrew Murray, then you have David Ramon, and then you have our presenter today, Dr. Andy Pepper. If you're here, you already know what this is about. This is the second presentation of the first in the webinar series that David Ramon has organised. And the purpose is to elaborate on discussions which have perhaps been initiated within the LinkedIn forum and have generated some interest. David took the initiative to see if we could go straight to the horse's mouth in this case, i.e. Dr. Pepper, and we're going to hear from him about his organic facies scheme and about some aspects of it which might clarify points for some people. So we'll keep everybody's microphones muted until the end of Andy stops speaking, and then we'll open it all up for discussion. So over to you, Andy.
All right, well, hello everybody. Thank you for listening in. I'd just like to firstly thank the organisers here, David and Andrew, for, well, firstly their leadership of the petroleum system analysis community within LinkedIn, and also for coming up with this idea and organising today's presentation. So this is round two of a presentation that's already been made. The plan ultimately is to, I believe, is to put it on YouTube. So let's proceed without too much ado. Okay, hopefully you can all see my screen fully now. So really, this is a conversation that came up through one of the many LinkedIn discussions, and it was really around, I think it was Nazim in Pakistan, who sent in a question saying, hey, apparently I've got type 3 kerogen, and I'm dealing with a rock that is Proterozoic in age, and how can that be? And so it seemed like there was quite a bit of confusion around the, around the classification scheme that the industry has used for many years. And so what I offered to do was basically to try to present an alternate view that certainly I've always used through my career, that I think avoids some of the pitfalls that we've learned now with the type 1, type 2, type 3 classification. So really this talk really is to explain it better in the sense of offering an explanation. History of where we come from, the approach, which is really more of a process-led rather than a classification approach, and the linkages that offers between the geology, of the rock, the organic geochemistry, the kinetics, and the fluid properties. I'm going to talk something about the model controls that go into the organofacies model, and then emphasize some of the difference between organofacies and type curves. So starting with the history, then, and as I get older, I do find myself more and more satisfied by going back to the sources of information and trying to get back to where was the original idea, where does the scheme that the industry work with come from, and how did it get to where it is present day before we go on to talk about the organofacies as something different. So really then the one thing to remember is that during the first half of the last century, coal and coal science was king, really, and coal was the energy source of the planet. And a lot of work was done in coal science. Even by the middle 50s, coal science was a very, very well-developed subject. And what we're showing here is a diagram that's digitized from the original by Van Crevelen in 1952. And what Van Crevelen did, by plotting out this on the vertical axis here, the hydrogen-carbon ratio of the organic matter from the coal versus the oxygen versus carbon here, basically plotted the evolutionary pathways of the basic components of coal. And those basic components are, as we know, a lot of woody materials. So wood is a mixture of lignin and carbohydrates. So during early diagenesis, lignin is concentrated, and then coal goes down this evolutionary pathway, losing oxygen and hydrogen, and then eventually losing hydrogen as it forms hydrocarbons in the form of obviously mainly methane in the case of the vitrinite here. But there are other components of coal here. He called it the exines. These are the leafy and spore and pollen constituents of coal, deposited in a much less oxidizing environment than the woody material in these raised mires where coal seams are deposited. So this is more the hydrogen-rich material following what he called the exinite pathway towards hydrocarbon generation. And then the final classification. So these are terrigenous environments. So these inputs are coming from the land essentially. But in the coal set of environments, in open bodies of water, we can often get these shallow lakes, which give rise to what are called boghead coals. These are algal-rich coals, and Van Crevel identified these are the most hydrogen-rich and oxygen-poor, and plotted an evolutionary pathway like this. And so coal is kind of a little bit more simple than the more generic set of environments we have to deal with in petroleum exploration, because it is a very much a terrestrial set of environments involving terrigenous and aquatic inputs. And so this is really the basis of where the subsequent work that was done to understand petroleum source rocks came from the work of the coal scientists in the 40s and 50s. So along came Mr. Tissot in the 60s and 70s, and this is a diagram digitized from his famous paper, where again he's plotting the hydrogen-carbon index, hydrogen-carbon ratio, atomic ratio here, and an expanded scale here of the oxygen-carbon ratio. And you can see here he's put some evolutionary pathways on there for what he called the 3 types of organic matter. So let's start with type 3. So this is a pathway that is somewhat similar to the vitrinite pathway that we saw for coal, for the woody parts of the coal. Coming back up to the type 1 area, this has got something somewhat similar to the boghead coal or the alginite environment. These are examples of freshwater lacustrine algal petroleum source rocks in here. And then the type 2 pathway is I've kind of colored these and grouped them together. These are a series of, in this case, they're clay-rich marine algal bacterial source rocks that are Jurassic through Silurian in age. And so you can see here that what Tissot did is he tried to map out the same evolutionary pathways for different kinds of petroleum source rocks, with an emphasis on understanding oil generation, as had Van Crevel done before. So if we have to kind of start to dig into this a little bit, there's a couple of things here that I think are a little different, though, to what Van Crevel was saying here. The type 1 pathway, for reasons that I don't think were particularly well explained, he's included these source rocks here from the Middle East, which are sulfur-rich marine kerogens on the same evolutionary pathway as the freshwater algal material in here, and there wasn't a lot of explanation for why. Alan Hoop from the IFP was on the last call when we discussed this, and he sort of pointed out, well, these were never meant to be strictly types of kerogen that were strictly common characteristics. They were essentially kind of trend curves, and perhaps that's a better way to think about them than to think about them as a rigid classification of kerogen type. The other thing we'll come to just in a moment is that if we look at these type 3 kerogens here, none of these are coals actually. So it's very different, although they seem to follow a similar pathway to Van Crevelen's vitrinite pathway. They actually are not. They are not non-marine source rocks. These are actually marine environments, and many of them come from the Dwolla Basin, which is an area that the IFP students worked on at this time in the late 60s and early 70s, and then marine sediments into which terrigenous material has been washed in. So let's take a look at some of the environment that give rise to this trend here. So we're going to look at the evolutionary series from the Dwolla Basin, starting up here where the least mature source rocks are, through the evolutionary trend. And let's take a look at the kind of organic matter that's in those source rocks, having said that they're not coals. So here are Van Creveland's trend curves. You can just see here, I've just put the same Van Creveland's trend curves on the same diagram as Tissot, and you can see here there's a kind of a type 1, type 2, type 3 matchup in a sense with Van Creveland's extinite, alginite, and vitrinite. But let's look at these type 3 kerogens, as I said, from the Dwolla Basin, and let's take a look at the basic organic matter as revealed by a GC. So what we're looking at here is just a concentration diagram. Vertically is the concentration of each compound, and we're looking at the alkanes from 13 through to 34. What we see is that those low mature samples I pointed to on the last diagram, they actually have quite a lot of low molecular weight marine organic matter in them. So really they are essentially those shallowest samples, and ironically those shallowest samples are the ones that most clearly define the type 3 trend here, are actually principally marine in biomass. They're dominated by this C17 material, and it's only the deeper samples that actually have this waxy material in here that really have a significant or dominant amount of terrigenous material in them. And so we do see then a little bit of a paradox here, that although this type 3 kerogen is assumed by many folks to be terrigenous kerogen material, often we'll see more examples in a moment. It's not. It's essentially some kind of bacterially reworked or oxidized marine material can appear on the type 3 pathway. And I think that's a source of a lot of confusion in some of the discussions that we've had in the LinkedIn communities. Is type 3 clearly does not mean that it's terrigenous or material or a coal. So along came Mr. Espicalier after Mr. Tissot's work on hydrogen and carbon, came and gave us this tremendous tool, the Eval tool, which really blew apart our ability to screen source rocks much more easily and quickly and cheaply than we did before. So we're looking at a modified Van Creveland diagram now with hydrogen index instead of hydrogen over carbon, and we're looking at oxygen index here instead of, sorry, my slides are jumping around, instead of the oxygen over carbon ratio. And we have two sets of source rocks I've put on the diagram here. Let's look at the orange ones first. So here are a set of source rocks that appear to be following the type 1 or type 2 pathway. So these seem to be hydrogen-rich organic matter that's following an evolutionary trend down towards the pure carbon trend down here, which would comply with a type 1 or type 2 interpretation. There's another bunch of samples over here which are following the type 3 pathway, and you might be tempted to think that those are terrigenous, indicating terrigenous material. And in fact, both of these sample sets come from the same source rock, which is a Silurian source rock predating land plants from North Africa. And what we're seeing here actually is that these are just simply the richer, more anoxic, well-preserved versions of the same organic input, the algal bacterial organic input, as we see over here. The only difference is that this has got a high sedimentation rate, is not as anoxic, and this material is getting degraded. It all has the same precursor algal bacterial organic material, which really, as I say, the type 3, and you see this also in older source rocks, in Ordovician, Cambrian, and even Proterozoic source rocks. You'll see things that clearly plot on the type 3 pathway, and it doesn't mean that they are terrigenous organic matter. And here's a little quiz. I know this is not perhaps the interactive environment to have a quiz, but I just thought I would throw up these data here and just, you know, if one went through the type 1, type 2, type 3 attempts to diagnose the environmental deposition and the organic matter inputs here, one might think that these samples here would be, if we went with that classical interpretation, these would be the terrigenous environments with land plant material in them, and that these would be the marine, high quality marine or lacustrine type 1, type 2 type of inputs from algae and bacteria. When we look at this set of sediments, it's actually from a Pennsylvanian set of sediments in the Denver Basin, and what you're seeing here is a sort of a cyclothem type of geology where we have non-marine and marine environments interbedded, and in fact the samples here are coloured. The size of the bubble reflects the organic carbon content. In fact, this largest bubble here, which is plotting on the, you'd be tempted to think this is plotting on the type 1, type 2 pathway, is actually the only coal in the data set. And in fact, these samples here are just simply lean marine, bacterially reworked and oxidized organic material. So the only sample that's different from all the others in here is, in deposition environment, is this coal in the Pennsylvanian, which ironically is plotting on the type 1, type 2, type 3 pathway. And actually it's quite common for coals to plot in this very ambiguous position over here, and essentially this kind of modified Van Crevelen diagram doesn't do as good a job for coal as the hydrogen carbon does. But just showing there that, you know, some of the pitfalls of taking this literally as a classification scheme, you're going to find yourself with some problems if you do take it as literally as that. So let's talk then about an alternative approach. And what I'd like to get us thinking about here is more of a, let's think about the process leading to the deposition of the organic matter rather than classifying it, and then from the classification trying to predict its behavior. What we're going to do is we're going to understand the process of the organic matter deposition, and then we're going to model the behavior of those organic matter characteristics when we look at our Kinetics model or our organofacies model. So not meant to discuss every item on this table here, but really what I wanted to draw attention to, there's a version of this in the first Pepper and Corby paper, similar version to this table. But what we're trying to do here, as you see along the top, is here are basically the 5 organofacies, broad organofacies here, and there is an organofacies descriptor, which I'd rather use a descriptor than a label, if you like, and really that descriptor benefits from a discussion of what are the principal biomasses going in. So in these marine and aquatic source rocks here, the source of the organic matter, sorry, my cursor is frisky here, wasn't doing this last time. Okay, so the algal bacterial input here is common to all of A, B, and C, and then really what differentiates those is the sulfur incorporation during early diagenesis. So when we have a low clay environment, and the H2S from sulfate-reducing bacteria starts to get incorporated into the kerogen and changes the kerogen type, the characteristics of the oil it expels, and also, as we'll see later on, the kinetics. And so there is a kind of linkage between environment. It's not really an environmental classification, but because environment leads to process, and process then leads to the understanding of the organic matter, then there is a kind of an environmental backdrop to the way this classification works, which is handy when you're working in conceptually in a frontier basin or in some other basin where you don't have a lot of data. You still have by following through the kind of logic in here, you still have a shot at understanding your organofacies. And so to move from the algal bacterial inputs then of A, B, and C to the terrigenous inputs, of D, E, and F. So D and E are often lumped together. Really, they just differ in terms of the resin versus cuticle input to the terrigenous organic matter. But essentially, you can think of those as the Van Crevelen's X-sign-rich material, the leafy, pore, and sporon type material that enriches many coals. And then this would be an example of a lignin-rich coal. Many Paleozoic coals are pretty much close to end-member organofacies F, and their principal component is lignin, which is the maceral vitrinite. So really, not trying to discuss every part of that table there, but just hopefully leaving you with a flavor that it's really a process type of description and not a classification based on plotting something on a particular diagram. And just talking about environments, just wanted to clarify, you know, I do think sometimes we confuse ourselves by using the same terms to mean different things. So when I say terrestrial just means the opposite of marine. So terrestrial environments can be both aquatic. If you're in a lake, that's a terrestrial environment where you have aquatic organic matter input from algae and bacteria in the water column. But also in these non-marine environments, we obviously have terrigenous environments, coal swamp type of environments. And then really just, rather than calling things, you know, mixed type 2, type 3, if we have a clay-rich environment with marine, like we had in the, for example, in the Dwolla Basin, if our principal biomass going in was, in many of those samples, was a marine bacterial algal material, then that would be a B. And if some D, E, or F terrigenous material is being washed in, then you know we could make this a hybrid of B and D, B and E, or B and F, depending on the kind of material coming in. So by looking at the end members and then mixing them later, I think we'll see that gives us a lot of flexibility in the way that we model kerogens, without having to go to things like custom kinetics, where we just treat everything as a completely separate new piece of organic matter coming into the laboratory that we have to define. Okay, so really then just my final sort of recommendations then with what do we do with the type curves. What I would say is that the type curves are useful. They tell us about indirectly, if we're using rock eval, about the hydrogen versus oxygen content of the organic matter. So it's the interpretation that flows from that can get very confusing. So hydrogen-rich organic matter, it's pretty straightforward. Just like on Van Crevelen's diagram, that can come from terrestrial environments or marine environments. So those environments have to be anoxic with well-preserved biomass, so that you preserve the hydrogen content of the organic matter. So generally, those environments are going to be aquatic. But in some cases where we enrich the cuticle and pore and pollen type of material going into a coal, we may find out also that we can have very hydrogen-rich or high hydrogen index coals that are dominated by those materials. And so we can have terrestrial material that is hydrogen-rich, just like we can have aquatic material that's hydrogen-rich. The hydrogen poor is more problematic in that if we know we have a low hydrogen and a high oxygen content, that can derive from two pathways. One is that it's simply lignin, just like Van Crevelen said. So it's low hydrogen because it's wood going into the environment, or we can have these degraded environments in the marine realm where we're taking essentially a completely aquatic algal bacterial biomass and degrading it down to a low hydrogen carbon content, in which case it looks like quote-unquote type 3 kerogen, but it isn't. It's just something, it's a different way of getting to the same chemistry. And so really what I'd like to still leave you with is I think type curves really tell us nothing about the precursor to organic matter input. They're part of the story of understanding how your source rock works and how you would adopt the prediction of its organic matter type to input to something like, as I'm about to show, the Kinetics scheme, where we have independent variables. Hydrogen index is not hardwired to kerogen type, so we can have, as we'll see in a moment, we can have an organofacies V environment that has a hydrogen index of 900, like the Basin, or it can have 600 or 500 or even 200 or 300, and still be essentially primarily an input from algae and bacteria with different stages of oxidation. So what I'll come to now is really, so how do we take the organofacies inputs and the organofacies scheme and then make useful models out of them? And so the first thing then is to discuss the inputs that go into those models. So this is really a description of what's underneath the Kinetics model, which is in the ZDWare family of software that many of us find useful. And it's about as simple a scheme as you can get, because it only has two components. So we're going to talk about a component which we're going to call oil, in inverted commas, which is the C6 plus components of the petroleum. And then we're going to lump the C1 to 5 components into something that we're going to call gas. So really what we're calling oil and gas here is not a phase, it's a molecular cut from 1 to 5 through C6 plus. So if we start with our initial source rock, initial quantities up here, we've got a number of quantities that can be defined by rock Eval. So the total area of the box here that defines all of the carbon in the source rock, including the inert carbon that doesn't go to form petroleum. There's some carbon in the initial S1 in the source rock. This is a material that's never fully condensed into the kerogen to appear as an S2 yield, but still is if you will, a starter in terms of an initial amount of petroleum that's always in the source rock, even when it's very mature, in very low maturity. And then reactive kerogen is really the S2 yield of the source rock in carbon terms. And there's an initial measurement here, which I don't think is all that common in the industry, but certainly, from my years at, starting in the BP lab in the early 80s, this quantity was measured on every single sample of any significant S2 yield, and that's the GOGI. So the GOGI is just the amount of gas generating kerogen to the oil generating kerogen within the S2 yield, and that's just derived by pyrolysis GC. You integrate the C1 to 5 yield in the S2, and then the C6 plus yield, and you ratio those two things, and it's like a gas-oil ratio, if you like, of the pyrolysate. So again, rather than trying to put things on a cross plot, type 1, type 2, type 3, and trying to diagnose oil proneness or gas proneness, my philosophy very simply is, well, why wouldn't you just go and measure it? And so those are inputs that go into the Kinetics model that may not be in some of the other models that are out there for petroleum. So then we have this process called generation. So generation takes the oil-generating kerogen and, in response to thermal stress, generates this oily material, puts it in a reservoir, if you will, in the source rock. It does the same with the gas-generating kerogen. It puts that in a reservoir in the source rock for this kind of organic carbon accounting. And then there's an additional, because source rocks are not closed systems, the oil that's retained in the source rock at higher thermal stresses is potentially feedstock for cracking to gas. And so there's a second source of gas here going into the model. You'll notice here that the graphite basically is the dead carbon. We saw in the Van Crevelen diagrams all of those pathways were heading towards a pure carbon at the end of the day, and inert kerogen is just the amount of carbon that would end up as non-generative, aromatized and inert material after all of the reactive material has been generated through this process. So we've just talked about generation there. So we've stored these quantities in the source rock, and in particular in the kerogen, and expulsion, strictly speaking, as I refer to it, refers to the release of these molecules from the molecular cages and molecular cages and tiny pores within the framework into which these molecules are born. So the molecules in a source rock are not born in the pore space where they can automatically make a fluid phase, they have to get out of the kerogen first off. And so this is this process called expulsion, which is really a sorption process. So these molecules have to work their way out of the kerogen and into the primary pore space. And it's at this point here where these gas molecules and these oil molecules can join together as a fluid phase with fluid phase properties like density and interfacial tension and so on. And at this point, once these molecules can join together in a phase, then the process of primary migration can occur. So primary migration, when it's efficient, results in a conventional petroleum system, because once the material is dumped off the kerogen and into the pore space of the source rock, then it's able to percolate away into the conventional system. When we have great storage within the source bed itself, then we have the capabilities to have an unconventional reservoir where the source bed itself becomes the reservoir for that fluid. So there's a difference between expulsion and primary migration. A great conventional system will have high expulsion efficiency and high migration efficiency. A great unconventional system will have great expulsion efficiency because you can't produce the oil and gas molecules that are dissolved in the kerogen. It'll have great expulsion efficiency, but it'll have inferior migration efficiency such that it holds back the fluid phase in the source bed layer as a reservoir. And really, so that's kind of just a little bit of a nod there towards the way to think about unconventional reservoirs, but also just to stress that the expulsion modeling I'm talking about, I'm going to be talking about for the rest of this presentation, is the expulsion and the release of molecules from the kerogen into the pore space where it can form a fluid phase. We're not talking about primary migration because we need additional modeling tools to address primary migration, because it's a fluid flow phenomenon and it is not a kinetic phenomenon. Okay, so the next thing I wanted to talk about here was really, we've talked about hydrogen index and hydrogen and carbon ratios. This diagram I think is really important because I think it explains, certainly to me, why source rocks are oil prone and why they're gas prone. So what I've done here is for different source rock layers, for different source rock hydrogen indices, I've calculated the amount of inert kerogen and the amount of reactive kerogen, and I've split the reactive kerogen into the oil-prone component and the gas-prone component here. And what you see here is actually rocks with low hydrogen index don't have lots of gas-prone kerogen. This is the paradox I think you have to appreciate, and that makes sense because to be gas-prone, a rock would need higher hydrogen-carbon ratio because gas molecules have a higher hydrogen-carbon ratio than oil molecules. So how can low hydrogen index kerogens be fundamentally gas-prone? They can't because of the hydrogen balance. What really makes low hydrogen index organic matter gas-prone is the fact that it has this massive inert kerogen component, which means that the oil that it's able to generate is very easily sorbed in the overall kerogen mass. So low hydrogen index source rocks are gas prone because they are low expulsion efficiency, not because they have high gas prone kerogen contents. And in fact, you see here that the rocks with the highest concentration of gas prone kerogen are the oil prone source rocks that have the highest oil generating kerogen, and these are efficient expellers of the oil because they have a small mass of inert kerogen relative to their oil generation capability. And so really high hydrogen index source rocks are oil prone because they're efficient oil expellers, not because they're much more fundamentally oil generative. So it's this expulsion efficiency that really is the key, I think, to understanding the true behavior of source rocks, and it's not really to do with the original quality of the organic matter itself, in the sense that the type 1, type 2, type 3 tried to suggest. Okay, so now let's come on to some model results. So we've seen the importance of the organofacies, of assigning the right organofacies. That gives us the kinetics. We've seen the importance of GOGI. as the gas oil generative component of the S2, which is a measurement, not an inference. It should be, in my view, something we routinely measure on all source rocks. We've seen the influence of hydrogen index, how that controls expulsion efficiency, and then the final ingredient here is when we thermally stress the source rock. Let's see how this different source rocks respond to with those different inputs. So we're going to talk about some model results now. So what I'm going to show now are the 5 organofacies, and firstly we're going to talk about, I'm going to talk about some typical or default hydrogen indices for these 5 source rocks. Now what I would like to stress is that I'm not trying to set up another type 1, type 2, type 3 scheme based on hydrogen index, and we'll see in a moment. I'll show you what happens when you change the hydrogen index of any one of these organofacies. But just for now, we're going to go with these typical hydrogen indices. So these hydrogen indices of the aquatic source rocks up here are typically 500, 600 or so. So let's talk about those first. And what you see here, let me explain the quantities. The dark green is the residual oil that is sorbed in the kerogen. The dark red is the gas sorbed in the kerogen, and then the light green and the light red are, we're assuming here, ultimate complete primary migration efficiency, and that the expulsion products are able to migrate away from the source rock and be accumulated in some giant bucket somewhere in the basin, if you will, where we can look at their gas-oil ratio. So this is expelled gas and expelled oil. These are not a closed system. This is the material that's able to migrate away as a petroleum phase, and this is the material that is sorbed and remains in the kerogen. So firstly then, let's think about generation kinetics, and for those of you that have modeled transformation ratio, then the outside shape of this curve is essentially the transformation ratio of the total kerogen. What I would encourage people to do is not to be content with just modeling transformation ratio, because as you can see here, it tells you really very little about the true behavior of what's going on under the hood, if you will, of the source rock. So what happens then is that as we start to generate, with generating the oil and gas prone kerogens, we reach a sorption limit, after which we're able to expel some oil and some associated gas molecules. And as we go through increasing thermal stress, what happens is that, sorry about this jumping around, is that the sorbed material then, as I mentioned before, becomes a feedstock for cracking from oil to gas. So you see here that at around 150 degrees thermal stress or so, we start to create another source of gas up here from the unexpelled oil in the kerogen. And so really then some of this gas is coming from the gogi, from the gas-prone kerogen that's being generated along with the oil. And then there's an additional feedstock of gas. And you can see that the expulsion efficiency is very important, because it's determining how much of this oil is left behind sorbed in the kerogen, and that oil can act as a feedstock for cracking to gas at later maturities. And in fact, you'll see that a lot of these aquatic source rocks, as much or probably more of the gas that's coming out is coming out from unexpelled oil cracking at later stages of maturation. Okay, so really then the only difference between A, B, and C, they all have similar hydrogen indices in these simulations, is the generation kinetics is pushing it back by about 10 degrees. So if you look at the sort of 50% conversion, there's about a 10-degree shift between the A, the B, I'm sorry about this jumping around, the A, the B, and the C over here. The C has a little bit tighter distribution of activation energies, which is why it's steeper, but really the only thing that's changing there, they have similar expulsion efficiency, but later generation. Coming to the DE and the F, it's sort of interesting. Now the DE is typically a relatively low, there's a relatively low expulsion efficiency environment, because the hydrogen indices typically are relatively low. So you see here that there's a much bigger mountain of that dark green stuff is building up in the kerogen before it's able to be released or expelled from the kerogen. And so we see there that there's a relatively minor fraction of that generated oil that's able to be expelled, and an even bigger feedstock of gas coming from cracking of that oil in the kerogen or the organic matter framework of the coal. And this is, to me, this conundrum. You know, people have made observations over the years that they can see from pyrolysis data that coals generate, many of these kind of coals, these waxy coals, generate a lot of oil, but the conundrum is that they're almost always generated with high GOR systems. If you take something like a classic oil-prone petroleum system like the Mahakam Delta, it's still 75% gas and 25% oil. And you can see here that just from this simple Kinetics run, you can start to see an explanation for why that is that although the coal generates quite a bit of oil, a lot of it is retained and cracked to gas at higher maturities. When we come to the F, so again, you know, you can do pyrolysis again of carboniferous coals that are essentially largely organofacies F. But what's happening here is that their generation kinetics is very late, so that the generation of that material is overlapping with cracking so much that you can see here that this bell curve of absorbed material results from the coal fails to reach that sorption threshold, and so basically eventually the rate of cracking exceeds the rate of generation, such that coal can never reach the coal can never reach the sorption threshold at any stage in its history. And so really then we have this paradox that when we pyrolyze this coal, we say, oh crikey, there's a lot of oil potential in this coal. Why do we only ever see dry gas deposits in the southern North Sea or wherever we have these types of petroleum system? And this is the kind of solution to the paradox: is it's generated, but it can never get out of the organic framework. All it can get out is the easily desorbed C1-5 material. And again, for those of you that are thinking about this kind of sorption problem, this red material, in the dark red material here, that is the resource of coal bed methane. Okay, so this gas here is sorbed within the organic framework, and you know, if we wait long enough and we stimulate the coal and so on, we can get some of that out. Some of the red material in here in these kind of source rocks in the marine is in shale gas. There is a later life component of production from shale gas, which is that dark red ribbon there you see on the diagram. But it's going to take probably 30, 40, 50 years for those shale reservoirs to drop pressure low enough to desorb the gas. But there will be some component of production of the gas from the sorbed material, but the oil component that's sorbed in the kerogen is not going to come out on any human timescale. And so one of the tricks of actually an unconventional resource assessment is to try to sort out what is sorbed oil in the source rock versus what is producible oil, and tools like this can often help. So I mentioned earlier on that this is not a scheme that's classified by hydrogen index. So hydrogen index can be changed independently of organofacies. And we see here on the top row, we can see what happens if we change the hydrogen index of the organofacies A source rock by around 150. In this case, you know, changing the hydrogen index of something that's already highly oil prone with a very high oil expulsion efficiency doesn't make too much of a difference. But what you see in the lower case there is again a classic. The hydrogen index of a coal system is very, very important to know as accurately as possible, because since you're close to the sorption threshold with a hydrogen index of 333, then you actually, by dropping 150 and going down to 183 there, you can see you've turned an entirely gas-prone, the coal into an entirely gas-prone entity, even though the generation behavior is exactly the same. So by changing hydrogen index, we change expulsion efficiency, and for rocks that have marginal hydrogen index, it makes a very, very big difference as to what hydrogen index we choose, as to whether we end up with a purely dry gas-prone source rock or a relatively rich oil-prone expulsive coal. So just a sort of another way of looking at that, if we take the expelled parts of those diagrams now and compare them, what I think is kind of fascinating here is that we see the difference between these oil-prone source rocks here. We're comparing the yields now per percent TOC rather than the absolute yields versus the S2 yield on the previous diagrams. And what we see here is per unit carbon, we see that these aquatic source rocks have very high oil yields per unit carbon and sort of, significant gas yields also. An example of significant gas yield coming from organofacies B would be the North Dome South Pars field, which is the largest gas field in the world, around 1,000 TCF, which comes from a gas-prone or a gas-mature Silurian source rock, just like the one that we saw earlier on in North Africa, where we looked at the HIOI diagram. And so the resources that come from these very rich oil-prone, initially oil-prone and later gas-prone marine kerogens can be very, very substantial. So let's come down now to the terrigenous organic matter. We see now that the per unit carbon, the DE source rock is actually a very poor, low efficient oil expeller. It still expels a significant amount of gas, and then really the F just expels the gas with no oil. I think what's interesting about these diagrams is that really it's not that the coals, the DE and the F, are better or more gas prone than the marine or aquatic source rocks. It's just that they're less oil prone. So really what's happening in those diagrams as we go from A through F is that we're basically losing oil yield. So it's not that coals are particularly good gas source rocks per unit carbon. It's just that they're less effective oil source rocks. And perhaps I don't know if you've thought about it that way, but I kind of find that an interesting way to think about these. And just again, the same diagram as we saw before, changing the hydrogen index, we're essentially changing the expulsion efficiency, and we're changing the in a unit carbon basis, we're also changing the relative oil and gas yields, just as we saw. So for the final couple of slides here, I just wanted to sort of come to a so what. And I mentioned earlier on, I do see a lot of really phenomenal modeling work going on, and often, unfortunately, it just ends up in a transformation ratio map, which, as you can see, compared to the information we were able to extract from those simple Kinetics models there, the transformation ratio map really isn't telling you very much that you need to know. And so once we have that gas-oil mix that we saw from a simple gas-oil mix, so C1 to 5 versus C6 plus, we have the pressure and the temperature of the source rock as it's been buried, and we can use simple correlations along with that gas-oil mix to produce these very useful quantities that people like engineers and geologists doing reserve estimates and predictions of phase and so on really need to know. And so the quantities we're able to predict then as we go through the same thermal stress diagrams. Sorry, oops. Sorry, my slides are jumping around again. Okay. Yeah, so the quantities we're predicting here on the first diagram, I'll just go through them all and we can follow them from there. The first curve at the top there is the gas-oil ratio in oil-filled units, standard cubic feet per barrel. So we see this source rock here starts expelling an oil with a solution gas ratio of about 100, and then goes through this. This is a double exponential curve. This is already a logarithmic scale, and we can see that it's going up exponentially. So there's an incredibly steep curve here with GOR versus temperature, and this is part of the reason why the fluid bands, the productive fluid bands within shale liquid reservoirs are so limited and so restricted, and the sweet spots are so restricted. Even on a gently dipping surface, you can see that if our sweet spot is around 3,000 GOR here, we only have a few degrees centigrade in thermal stress terms, where we have to get to exactly the right part of the kitchen in maturation state in order to predict where that fluid is. And also, once we have the GOR and the pressure temperatures, we can predict things like the viscosity. So these Class A systems here, they have a lot of heavy compounds in them, which go towards a heavy API. We have a heavy oil density and a low GOR. We have a high viscosity, and so we see again the viscosity is responding here until we get to about 150 degrees where we have essentially gas viscosity through the rest of the regime. We're also predicting the density of the fluid, and also here even the interfacial tension. So again, once we have these, even a simple two-part oil and gas mix, we can do some really useful things with that. And really, we'll see here that the differences between A and B and C, again, not so dramatic as the differences between those aquatic source rocks and the terrigenous ones. So here, for example, the coal, because it expels later, paradoxically, the expulsion products are going to be higher quality. So we end up with a higher GOR oil, a less viscous oil, and one with a lower density, because we've kept the generation products in the source rock for cracking much longer than we did in the efficient expellers, which are A, B, and C. And then our friend there, the organofacies F, never gets to expel any compositions that would be of a fluid or bubble point type of fluid, and so they're expelling fluids that would only be on the gas side of the phase envelope when it comes to migration. And then on the last slide here, then really looking at the effects of the GOR, the results in terms of GOR on the change in hydrogen index. So there's a little bit of careful what you ask for there. So you may think that you're doing yourself a favor by putting a really high hydrogen index in for your source rock when you model, but the price you'll pay there for that with earlier expulsion comes a lower and lower GOR, a higher and higher API gravity, and a higher and higher viscosity and density of the subsurface fluid. So this explains why, look at places like Maracaibo Basin, many of the Middle Eastern oil systems in Iraq and so on. You have these very low GOR, dense fluids, so they're very abundant, but they're also very low quality and of less intrinsic value in terms of dollars per barrel, with discounts for gravity and sulfur and all these other things. And again, paradoxically, looking at the DEs, I think it is an interesting paradox that the lower quality source rocks will give you a higher quality stop tank barrel in terms of your oil assay yield. So because we're holding compounds in the kerogen longer and cracking them away to smaller compounds, then we're generating a much more valuable product. The one that's expelled, even though there's a lot of gas with it, often will be a lighter oil and a more valuable product at the end of the day. So just to conclude then, so here's a few of my sort of tips, do's and don'ts. And so just coming back to the original thing that spurned this, David Ramon's suggestion that we did this was, what can we really do to clarify what to use the type charts for? So don't use them as a silver bullet. Don't try to use them to predict the organic matter input or the environmental deposition, but use them along with all the other data to build a picture of what is your source rock like. And when you come to modeling it, is the low hydrogen index caused by simply by bacterial degradation and oxidation, for example. So the new approach then, what I've said again a number of times, is that the organization scheme does not rely on a hydrogen index to define the end members. You have to use the geology and the geochemistry of the source rock, including the type information, to come up with a hydrogen index number and which kind of kinetics and which kind of organic material you think are going to be in your source rock. A plea that we should all start measuring GOGI routinely on all samples, as the BP lab were doing routinely in the 80s. I see a lot of folks worrying about generation kinetics. You saw there that those kinetics curves only shift by about 10 degrees centigrade as we go through the major organofacies. So worrying about whether your source rock, has a 5 degree difference in generation behavior is I don't believe is really the root cause of understanding how your source rock will behave. So for me personally, kinetics are a dumb problem, and I would rather focus on getting the HI right and the overall kerogen mix right in terms of a process model feeding into something like Kinex. So in terms of the new approach, the kind of results that we would get that would be different the type approach is that because HI is independent of organofacies, then any source rock can become entirely gas prone if you lower the hydrogen index enough. I know many examples of source rocks where you look at the visual kerogen assemblage there, and it's clear that there is no terrestrial material in there, yet the hydrogen index is very low, and it's just bacterially degraded, low quality algal bacterial material. At hydrogen index less than 200, basically all source rocks become gas expulsive, because no matter what their initial potential is, the expulsion efficiency just shuts off efficient sorption of oil molecules from the kerogen, and so everything, it's only the gas that can escape from the kerogen, so everything becomes gas expulsive. And then hopefully I left you with some demonstration there that simple models that predict GOR can then go on to yield very powerful and useful fluid predictions when they're linked to fluid property correlations. And for me, that is a step that we should all try to take beyond modeling transformation ratio or some of the more traditional modeling approaches. And I've seen those kind of models yield really very powerful results that engineers would need for their evaluation and so on. And at that point, you really are starting to integrate petroleum systems with the overall, much more with the overall valuation and evaluation of the play once we're talking to our friends, the engineers. So really, that's where I wanted to leave it today. Thank you very much for listening. And I just a couple of thanks there, David, Ramon, for suggesting we did this thing, and to Andrew for organising this particular version. Z2Ware for Xiong allowing me to use the Kinetics software to demo that, and Hess Corporation Management who allowed me to use some of the slides that we used in the old petroleum system class that we used to teach at Hess back in the about 10 years ago or so. But slides I believe are still as relevant today as they were before. So thank you very much for your time, and Andrew, I'll invite you to open it up to the discussion. Thank you.
Thanks again, Andy. That's great. I'd rather than open everybody's microphone for questions, if I do that, the accumulated background noise from 20 odd microphones will be too loud. So what I suggest we do for questions is that if people want their chat window to just write question or comment, I'll see that pop up. Make sure you address it to everybody, and then I'll unmute your microphone, or you can unmute it yourself and ask that question, so we get one at a time and we don't talk all over each other. Can we try it that way? Not hearing anything in return. It's probably because everyone's microphone's off. Hang on. And that's what we've got everyone's microphone on now. Background. Anything you want up again. But if you want to send a question or a thing, just put it in the chat window and I'll call you in order. Thanks.
Unmuted.
So Andy, may I ask a question then?
Go ahead.
So thinking about those plots from Kinetics, so how well constrained do you feel these calculations are? So since these results are dependent on what's coded in, what sort of a model is coded in Kinetics. How, for example, how the expulsion efficiency depends on HI. How well constrained do you think this is?
Yeah, good question. So yeah, one of the things that I guess I would say has been a little bit disappointing since this kind of model was initiated back in the late 80s in the lab at BP, which is where it came from. very little work's been done on the sorption capacity of kerogen. So I know at the same time that we were thinking about it, there was work done by the Exxon team, Sandvik and folks were working on it. People have come up with this kind of idea, rule of thumb, for around 100 milligrams per gram of C6 plus material is a kind of a default number for the sorption capacity of oil within the overall kerogen framework. It would have been great if a whole body of work had sprung up after that, and we'd actually had some better numbers around that. So there is some work on the gas components from coal bed. As you can imagine, coal bed methane production is a desorption process, and so the coal bed methane guys have worked on multi-component sorption, where you can see that the C1 comes first, and then the C2s, and coal seams eventually will produce C3 and C4 later in their life as you're able to pull on the more heavily stored materials. But it would be great if we were able to generate some better numbers around that. So that kind of number, the sorption capacity, is partly indirectly derived from plotting things like S1 versus carbon for source rocks, and looking for relationships. And that was the way in the third paper, for example, the Pepper and Corvey third paper. There's a correlation there from the North Sea, where you can see that there's a very strong linear relationship at different levels of thermal stress, from which you can estimate the maximum sorption yield is around 100, and it's just over 100 milligrams per gram. It would just be great if we had more information around that, because in addition to the hydrogen index, it's that number that determines how easy it is for the oil molecules to get away from the kerogen framework where they originate.
So
what I'd encourage people to do is to not to just use that number as a complete default, and to sort of vary that. I mean, you can produce similar things for the Basin shale, for example. There's some beautiful data for the Basin that shows, I mean, it's around the high 80s or 90 milligrams per gram for the Basin. So that was a little bit different to the Kimmeridge clay, which is the North Sea data set. It would be just, even if we derived some data by organofacies or by whatever criteria to refine that number, would be really helpful, I think. Let's have a library of sorption coefficients.
Mm-hmm.
Is that where you were going there?
Yes, exactly. And I was wondering if so you are showing a difference of, say, plus minus 150 on the HI scale. I'm wondering, in terms of uncertainty associated with these relationships, sorption relationships, how much of HI would fall within the range of uncertainty, roughly, or what is a meaningful variation step that makes sense to kind of explore? Is it 100 or is it 50? Or if I use 50, am I already playing within the range of uncertainty that I cannot resolve anyway? So
right, yeah. Well, I think again, the sampling of source rocks is a really is a separate subject in itself, and there's a kind of a workflow within Kinetics also, where instead of just choosing an average, which I'm not advocating here, you can actually model each layer or each sample of a source rock. If you have 100 samples, you can model all 100 and basically have a composite result of those 100 simulations, instead of averaging them first and doing one simulation. So I think by the time that you've got a large data set like that, then you've already captured the variability in your hydrogen index data, and so really I think the remaining I would say the remaining sensitivity would be around your sorption coefficient if you have a lot of data. If you're in a frontier area, then I think, I chose those values 150 plus or minus for the DE, because, I mean, those are, you can look at DE systems around the world and you can find coals that are at both ends of those spectrums and still essentially DE. Andrew, I mean, you've done a lot of work in coal systems. Maybe you have a perspective there. If I could drag you in.
Yeah, just to be honest, I was just watching the screen and trying to figure out how to control things, so I wasn't listening that well. But,
Okay.
yeah, I think just to come back to a comment about the importance of the sorption capacity. I know that Andy, you and Ziong and myself to some degree have talked about that already. Certainly it would appear that for coals the more typical number is around 50 milligram per gram TOC. In fact, in the Cooper Basin it looks like we're more like 30 to 40. Do you have any more feeling of that? You were saying a few moments ago that you'd like to see a library, if you like, of absorption capacity, but of course we're only measuring what we can see in S1 then as well, and for coals there's a lot of gas, so we're only underestimating it anyway when we do that.
Yeah, I think quick to coals, and I think the problem with coals is that if you look at progressive extractions, I think the problem you have with getting to the correct S1 yield of a coal is that it is so closely bound within the organic matter framework. They're just less pyrolyzable, if you like. And so the way I get around the coal problem is that if you model instead of modeling hydrogen index versus thermal stress and calibrating to that, if you model what I call QI, S1 plus S2 over TOC, what you find then is that if you're able to match to that, then you've accounted for the fact that the pyrolysis didn't do the correct division between S1 and S2 in the coal. So I actually don't believe that absorption coefficients are 50 milligrams. I believe that's part of the if you like, the volatilizability of S1 in a coal is different to that in a source rock with a more open mineral framework.
Okay.
And if that helps you, but so I wouldn't put a lower. I certainly would not put a lower value in a coal for that reason, just because you don't see the S1. Because I think the S1 and the S2, basically, that's what I'm saying.
I think there's a follow-up to that will come later, but I want to give other people a chance to talk. I'm just looking at the list of questions here. The first one in the list is from somebody who has a screen name of Tech Notify. I'm unable to unmute the microphone for obvious reasons. I can't override anybody's microphone, otherwise I might listen to them shouting at their dog or something like that. So if Tech Notify is listening and you have a microphone, if you could unmute it. Otherwise, I can read your question from the screen, which is when organofacies A rock is highly oxidized, should its kinetics also reflect that change from an A to a B, E, or F?
That's a great question. So what I can answer there is from my own experience. Let me talk about one of the data sets that went into the organofacies B correlation. That data set was from a small basin in the UK called the East Midlands Basin, and there you have carboniferous source rocks that are they're deposited in a they're lower carboniferous source rocks, marine. They're deposited in a marine gulf, and you have to date that there isn't a shred of polymorph type material in there. You have to date them with conodon. So it is a truly restricted organofacies B environment. There's no terrestrial material going in there. Those went into the kinetic data set, and they have a slightly different GOGI. Remember, we're optimizing the kinetics of the gas generating and the oil generating carriages separately here. So the difference in their generation kinetics is accounted for by the fact they have a difference in GOGI. So the actual oil generation kinetics of the net oil generating component of that source rock was the same as far as we could determine it. It was in the same range of scatter of the range of high hydrogen index source rocks that we saw. But the trick to that is that you're not modeling bulk carriage. We're not modeling a bulk transformation ratio curve here. When you model the separate components, you start to see more commonality in those components, because they will have a different, those two simulations will have a different transformation ratio curve, but the individual kinetics of oil and gas in them will not change. It's just the proportions of the oil and gas generating carriage it changes. Does that explain that right, clearly?
Sounds okay to me, Andy. What the person who asked can reply. So the next question was from Fauzan Arif, and Fauzan does have his microphone on. So the question is about DE coals and GOGI. Do you want to speak, Fauzan?
Hi, Andy. Thank you very much for the presentation. Can you hear me?
Yes, I can. Thank you.
Okay.
Yeah, thanks. Great to hear from you.
Yeah. My question is about, as you know, Southeast Asia tertiary coal is have potential to generate oil. So DE coal, if we don't, I do have some DE coal with different HI value. For example, one drilled on the basement high, which is lower HI, and then one in the deeper center of the graben, which is higher HI. So I don't know, is that a function of because you are in the high, so you got more oxidized, so you reduce your HI during after the organic material deposited, or is that because you have more aquatic organic material in the deeper center than on the high? And if we don't have and then the next question related to that, if we don't have the GOGI for the gas oil index generation index for each sample, so can we just model that, or is there any catalog or publication that showing that which HI 200 your GOGI should be this, and then if you have higher HI then your GOGI should be this, so you have like curve for if you don't have the GOGI number for each sample, and then that's all. Thank you very much.
Yes, thank you for that question. Both questions very good. So Andrew will very much identify with this question about, is there a correlation between GOGI and HI? There is a very broad one. So if you don't have that data, then there is a correlation in the Pepper and Corvey paper number 1, which if you're using Kinetics will default the GOGI for you if you choose the organofacies and the HI using those relationships. So yeah, you can go to those diagrams in Pepper and Corvey 1 if you don't have the GOGI data. Your other question was really very interesting. So I think your former explanation that you have a higher, more oxidizing sort of upper delta plane environment on the high and a more submerged, mire environment in the basin makes good sense to me geologically. What I would say about introducing aquatic material into a coal is that generally, as far as I can determine in the coal literature, these boghead coals, the algal coals, are very, very discrete, different environments, and so you don't tend to find coal seams that have, within a seam that suddenly go to a boghead and then back again. So you do see alternating amounts of terrigenous, waxy resin, cuticle pore and sporran versus wood in an individual coal seam. But these organofacies see these little floodplain lakes are very discrete environments. So it may be possible that you do have some of these in your overall architecture. I don't know your basin well enough to know whether introducing a few layers of C in your DE description is the right geology or not, or whether it's just a variation in the amount of your hydrogen index, if you like, within the DE. Do you have any data to confirm that the coals do have any kind of aquatic material in them? I think that would be very unusual in my experience.
Sorry, you mean plastic material within the coal? Yeah, it is. Is that? Sorry, what's the question, Andy?
Yeah, do you have evidence for separate coal seams that are these boghead coals, like the organofacies C, that have a very different environment entirely from the raised mires that deposit the coal seams? Do you see that in the geology? What I'm saying is I don't think. Yeah, go ahead.
Yeah. Sorry. Yeah. What we know is we have several. Relatively few penetration, but in Natuna, East Natuna Sea, and then goes to Ho Chi Minh. Sorry, was it Nam Chon Son Basin? So based on that data, the well that drilled on the regional high, I mean like a major tilted fault block, has lower HI, and then the one that drilled deeper part in the deeper part of the basin will have higher HI, but the continuity of the coal seam is not. It is very sparse exploration well, so I'm not sure if we can correlate, but yeah, I think that's all I can say. Maybe.
Do you have any oil data? Do you have any oil data because if you had organofacies C interbedded with the coal that was making the difference, then you would expect to see some waxy coal that had, for example, low pristane phytane ratio and different biomarker signature versus the classical high pristane phytane and other indications of a terrigenous organic matter input. Is there any indication from the oil coming out of the basin that it's a C versus a DE?
I can't really remember exactly the pristane phytane ratio, but I think it's the conclusion is it's purely coal. So even there is a biomarker called anthracite, something like that, which is indication of the coming from coal. So I think it's strongly we can conclude that it's all coal derived oil.
Can I make a comment on that, if you don't mind, Farzan and Andy?
Sure.
First of all, just getting back to Goggy, I think this is something that I've badgered Andy about shamelessly over the years, but the correlation you speak about in the paper includes all the kerogen types. If you isolate out those which are DEs, I would argue there's zero statistical correlation between Goggy and HI, and that's our experience locally as well as in the Southeast Asian systems generally. You just have to have PyGC if you want to get a good idea. Having said that, I don't think that's the major factor for gas versus oil. It is actually the expulsion behaviour that's important, as Andy has elaborated upon, so I wouldn't sweat too much about that. The second point that Andy's referring to is, are you seeing any evidence of a lacustrine contribution to the oils, which might suggest you have some algal source component as well? Now, I can tell you that there's a very big problem with that approach we've become aware of over the last few years, and that is that lacustrine organic matter, when it contributes its biomarker signature to an oil, is very bland and hard to pick out, whereas the terrigenous signature is very strong. So if you mix an equal amount of a oil from a lacustrine source rock, a C-type source rock, with a DE-type source rock, you'll see all the oleonanes, you'll see all the bicarbonate, you'll see all of those things, and you'll conclude that it's all coal sourced. That is not the case. You can have lacustrine beds, and they do commonly occur in small lakes and so on in amongst the facies, and you just won't see it unless it's there in very dominant form. So just be aware of that. There are some things you can look for to deconvolute that. I don't think there's time today to elaborate on those things, but there are some tricks you can use in the geochemistry to stop falling into that trap. I do think there are quite a few basins which are attributed to coal source primarily, and there is actually quite a strong lacustrine component contributing, and they end up with low GORs than you would expect in those systems. The Gippsland Basin, in fact, may be a case of this, where you have a GOR for the system of around 2,000 standard cubic feet per barrel. It's much lower than you would expect for a coal source system.
Yeah, it is true. If you look at basins like Central Sumatra, they have an extremely low gas oil ratio, and the coal source systems are really, it's an order of magnitude difference. So as Andrew says, sometimes the appearance of a really low GOR oil is almost pointing to the fact that it's unlikely to come from a DE or F type of material.
Yeah, I think it's good to look at the bulk properties first of the oils before you start thinking about the biomarkers. I think one of the good things about the Pepper and Corby scheme is it gives you a pretty good idea what kind of GORs and APIs you should expect for a given source rock assumption. And I would start with that, and then only then look at the first parameter to look at is always pristane phytane. It's the strongest discriminator. It's a bulk component, so you don't get trapped by being biased by trace components. Only then go and look at the biomarkers after you've worked all that out. That would be my approach.
Yeah, I agree with you on that, Andrew. I would just say as well, I do see a lot of people. You know, there's a kind of an industry guideline out there that pristine phytane greater than 3 is significant terrigenous. I actually think the number's much higher. If you look at the pristine phytane of unequivocal coal-sourced systems, it's more like 8 or 9 or 10. Yeah. And I do think there's a lot of these more vague environments. Maybe a floodplain lake that's got, you know, the CDE, you know, these mixes of material in there that, and I think things like tricyclic fingerprints as well have not been used as well as they rigorously as they might have done. And like Andrew says, you know, you can get oleanane. I can show you oleanane higher than hopane in carbonate sourced oils in the Far East. Some of these plant markers that people talk about, they're kind of wild cards that you need to be very cautious about interpreting any significant input from them. In fact, I think in all my time in Indonesia, working in the East Java Sea, the highest oleanane I ever saw was in a deep water lean marine deep water oligocene sediment that had nothing to do with the actual petroleum system. So if you look at many coal systems, the oleanane content is not as high either. So yeah, I agree with Andrew. I'm just trying to reinforce that I don't think I agree. It's bulk properties that you should try to look for, and I think there is a lot of misdiagnosis done by going straight to biomarkers and trying to get organofacies from biomarkers. There are many solutions and many pitfalls, I think.
Yeah, Andy, if you'll allow me to share my screen for the moment, I'll show you the audience, the figure that I sent you earlier, which shows the pristine phytane discrimination. I agree with your point. I think that 3 is the minimum by a long way, and if I can share that for a moment, I can show the audience that.
Yeah, absolutely.
Let's see if I can make this happen. Give me a moment.
You can take my screen away.
So you guys seeing now a figure with some histograms and some red bars on it?
Not yet.
Okay, let me just see if I've got the right screen on. How about that?
Yes.
You can see that all right?
Yep.
Okay, so in the top left-hand corner there, you can see pristine phytane. This is from a statistical analysis of the GeoMark database of around 2,700 oils, which I went through and laboriously classified myself according to a bunch of parameters, and also the geology of the area and the literature. And you can see that for a DE facies, the oils that come out of that have that red bar, which is the mean plus sort of standard deviation. And the ones down the bottom there, below 3, are the ones that Andy's referring to, which are probably actually misclassified as coal source for various reasons. In there you will include, for example, a lot of the outer Niger Delta stuff, which I'm pretty convinced comes from a marine source rock, but is often misclassified as
absolutely, yeah. Yeah.
So I'll just get off that so that you have the screen back, Andy. Just let me do that. The other, just while we're on that comment too, I'm mindful there are other people wish to speak, so I don't want to speak too long. Just one moment, I'll get the screen back to where it's supposed to be. Okay, so it should be back on your screen now, Andy.
Oh, okay.
I hope it is. Let me see if I can get it back to you. It is.
Can everyone see my screen?
I can't yet. Okay, let me just see if I can do it here.
I haven't got the share my screen button up. I haven't seen it.
No, I can't seem to do it.
Now I see it. Now I see it. Hang on. Got it. Okay.
Well, just while that's coming up, Andy, the other mention you made of the Central Sumatra oils. That's an example of the opposite situation as far as land plant versus lacustrine biomass is concerned. You know, these are big lakes, and around them they have lots of plants. And if you look at most of the Central Sumatran oils, you'll find they have either no oleanane or very little oleanane. And the reason for that is because they are strictly freshwater environments, and in the freshwater environment you do not get translation of the oleanide precursors into oleanide. What you get instead is aromatic oleanoids, which are very abundant in those, and you can go looking for them. But you won't see them in a standard biomarker report.
Right, okay. Interesting.
All right, so now we have, just looking down the list, Lucas Krasinski, are you still there, Lucas? I'll turn your microphone on.
Yeah, I'm still here.
Okay, so I'm just looking at the list now. There's one more comment that, that my former colleague at Woodside Innes has made. If we'd like you to make some comments on changes, we'd like you to make some comments on changes in GOGI and HI in DDE type source rock when high gas maturity is reached. In other words, should we model lower HI and reduce their capacity to generate oil and liquid? So I'm not sure I understand that question. Do you understand it, Andy?
No, let me see if I can. Can you read it out slower?
Yeah, look, it's in the chat window, so it should be, if you can see your chat window, you should be able to see it.
Yeah, let me see if I can back it out.
This is from Inez Melendez-Morgan.
I can't seem to scroll down through the chat window now. It seems to stop scrolling.
Okay, let me just read it to you again.
Could you read it again, just slower?
Yeah, I'm just going to have a look and see. Inez doesn't seem to be on a microphone anymore. So what it says is, if you can make some comments on changes in GOGI and HI in each of the organofatty source rocks when high to gas maturity is reached, should we model them lower HI and reduce their capacity to generate oil or liquids?
Well, I think if you're looking at when high maturity is reached, I mean you've already set the. Yeah, I'm not sure if I understand either. In this example that's on the screen right now, the DE example, I mean you've already set the hydrogen index at the beginning of the simulation, and so really you should be matching to HI as one of your calibration methodologies, because this model will also tell you what the HI at that maturity should be if you assign the correct HI and GOGI, right? So you have to have the starting HI, and the starting GOGI will, because the oil and gas generating components, the gas generates later, your HI versus thermal stress or RO profile should from a highly mature sample should really help you to diagnose that you've got the model right. So I mentioned earlier on about plotting, for example, QI or S1 plus S2 versus thermal stress, or S1 S2 normalized to carbon. I don't know if that answers the question correctly, but if it's about how do you use mature data to make sure your model is correct, then yes, I would definitely encourage people to do that. The other thing I often see people do is because they're in Southeast Asia, they think, well, okay, it's DE. Well, for me, I would say DE and F are just N members, and I would feel free if the kinetics is telling you that you've got a system that has generated some coal store soil, but you don't have that much of it, and if your HI versus thermal stress is a very slow trajectory, then that's telling you it's not a DE. And so I don't think you have to have this sort of dogmatic view that just because you're in Southeast Asia, it all has to be N-member DE. And I've seen some coals in Southeast Asia in the tertiary that I believe are better described as F rather than DE. And maybe that's to do with their deposition environment, maybe their upper delta plane or some kind of more oxidized environment locally. I don't know, but don't always assume that it's DE and that you know the kinetics are wrong for DE, because they might be pictures of DE and F. You look at the coal scientists; there's a complete solution series between wood and leaves, right? And that's what you're looking at there. So don't be afraid to a DE and an S together if that's really what describes your HI profile best.
Yeah, yeah, I had the same experience, Andy, I'd have to say. All right, well, look, we're at the end of the list of people who've commented, at least in the text window. So if anybody else has some other comments, I'm going to turn all the microphones on now. So if anybody else wants to speak, as they say, now or forever hold your peace. Otherwise, we'll finish off and see the recorded version of this, or the previous one, perhaps, on the web and link.
I just want to say anyway, Andy, thank you very much for hosting this. I really appreciate it.
No problem. It's your time. That's you put the most time in this, Andrew. So thank you.
I think it's good now. So, does anyone have any questions for Andy?
Can you hear me?
Yes.
Yes, I can.
Yeah, Chris Cornford from IGI. Hi, Andy.
Hello, Chris. How are you? It's a while since we talked.
Very well, very well. You know, sitting out here in grand isolation with a number of colleagues. I was just going to put in a plea for this idea that you can define organofacies. The original definition was that it included all information on the organic content of the sediment, rather like lithofacies, by analogy with lithofacies. And the amount of information you can get from just isolating a kerogen, smearing it on an optical slide and looking at it in transmitted and fluorescent light solves many of the problems that you've illustrated as being unable to be solved using purely Eval and TOC. Do you have a comment on that?
I totally agree. So just as the coal petrologists, I mean, they've used the coal standards used every scheme from basic observation of the the vitrains and the claranes and the hand specimen definition of a coal, and then looking down the microscope at the macerals, which are really the equivalent of the mineral in the inorganic sense, and just putting it all together. And I think this integration, just putting it all together in a geological way is, I think that's what you're saying too. It's interesting, coming back to those Dwolla samples, it is interesting if you read back through Bernard Durand's original papers, it's interesting that there isn't that much vitrinite in those samples. What there is amorphous kerogen. And so I think this is one of the areas where, I think again, visual kerogen's very helpful usually. Sometimes amorphous kerogen can be a lot of things. And so I think rather than I'm just agreeing with you. There's no silver bullet here, and it's about describing a rock basically. Maybe we describe it with slightly different numbers and approaches than regular geology, but you're still describing a rock.
And slightly ironically, Andy, field work has has discovered lots of oil seep in Dwolla, and the drilling has come up with oil-related liquids and associated wet gas. So it was, as a type 3 example, the Dwolla Basin is not ultimately proved to be gas prone.
Right, absolutely. So there's dry gas prone, and then there's oil prone, and then there's in the middle. And I think there have been some arguments historically in that area around the behaviour of coals, and some people have sort of staked themselves out and said, well, there's no oil coming out of a coal ever, and I just don't think it's like that. I think coals are highly variable. Some of them are the Paleozoic coals. I've not seen any concrete evidence that a Paleozoic coal anywhere has yielded C6 plus material. But in theory, if one were high enough quality, perhaps you might. So I think again, the ability to model these things these days is just great, because we don't need to choose these end members and sort of stake ourselves out on it's this type or that type. We can just simply model the results and also the sensitivities of the results too. Well, you know, how much does it matter if my hydrogen index changes by 50 degrees centigrade versus how much does it matter if my generation kinetics move by 5 degrees C? And we can sort of satisfy ourselves, I think, which of those things are the things that we should be focusing and working on.
Okay, thanks for that.
Yeah, thanks for the input. Appreciate it.
Yeah, can I ask everybody, if you start talking, could you please turn on your camera so that we have a little bit more lively interaction here?
I'm getting a view of the camera as well.
I was going to throw out something, hopefully that might cause some discussion. I don't know if Nazir is on the call, the geologist from OGDCL in Pakistan that started this kind of conversation on the LinkedIn. But does this make sense to a non-expert geologist in terms of a different way to think about it? Does it make sense now that your Proterozoic source rocks plot as type 3 kerogen? Because I think that was causing either him or his management, especially who are sort of vested in the old way of thinking about things. His management, I think, were telling him, well, hang on a minute, it can't be type 3 because it's, you know, there's no coal there. So hopefully this is, if we can explain it better, then maybe it's helpful in situations like that. Have other people come across difficulties in explaining these kind of oddities in the classification?
Hi Andy, it's Wayne Knowles here.
Hi Wayne.
Hi. Yeah, just kind of touching on that subject. It's more really a word of warning that you could put out to non-geochemists when interpreting pyrolysis data. There's a lot of cases where I've seen very lean or even non-source rocks that have been analysed. The data have been put on a Van Krevelen diagram, and you know, because there's hardly any organic matter in there, everything seems to plot as type 3, type 4, and people start jumping up and down saying, well, you know, we're meant to be in a marine source rock environment, and we've got everything here, you know, plotting as you know, coal. So
yeah,
it's, you know, it's a real word of warning that, you know, I think it should be pushed to non-geochemists.
Yeah, so I think that, you know, for me, the power of the basic conclusions of the type classification are, if you remove the environmental and organic matter input, the empirical observation that low hydrogen index source rocks are gas prone is absolutely right. You know, the question is, don't tag on all the other stuff, that's been tagged on. It was actually interesting. I think probably the first person to point this out was there was a paper by Colin Summerhays in the DSDP volume on Lake 77. I've been writing a report on the Gulf of Mexico deep water petroleum systems recently and looking through that, and that was the first report actually in the DSDP volumes themselves, where he pointed out that the low HI material that was plotting in this region, when you looked at it in terms of the organic petrography, was really, there was no evidence of plant material in there, and it was kind of degraded aquatic algal bacterial material. So, fully agreeing with you. I guess that, you know, there's also a broader question here about how we go forward as a community. I think if we want to make this more explainable to our colleagues, especially the non-experts, then it's sort of like we got to kind of get together and decide what is the new way that we're going to describe these rocks, because there's a lot of old stuff out there that's confusing people, and until we can kind of come forward with a sort of unified new way of doing it, maybe that's something we should focus on as a community. And I would point to the geophysical community are really much more together on this than the geochemical or petroleum system community. So when they talk about a type 1 or a type 2 or a type 3 AVO, they all know definitely what that means, or what polarity is the seismic and so on. So maybe there's a kind of a I don't know if it's a consortium or some sort of thought body that we could put together that would say, well, this is how we're going to address these things in the future as a community, and then will both help ourselves and will also help our colleagues who are trying to understand this stuff like we are.
A fantastic thought. Geochemists and geophysicists working in harmony.
Well, with the unconventionals, I think we've managed to pull in some of the petrophysicists. So you're halfway there with the petrophysicist. Someone that's looking at rock properties and of organic rich rocks. You suddenly find there's a kind of a, you've got a buddy there in the system, yeah, as you probably know.
All right. Well, thanks very much, Andy. Nice presentation.
Thank you very much. Glad you enjoyed it.
Hi, Andrew.
Yes.
Andrew, do you hear me?
I can.
Hi.
Okay. Just point of clarifications. You hear me?
Yes, I can.
Okay. Just a point of clarifications. Actually, at the very beginning, the types of organic matter has not been defined as classifications. They have been defined reference series. I think it has been a shift in the interpretation. Marine and terrestrial. Regarding, I want to congratulate you for your presentation. And I'm just wondering if there is not a way to reconcile the concept of the chemical compositions, which is represented by the hydrogen content, oxygen content, and so on, with your classifications. Because you put a lot of emphasis, and I agree with you, on the expulsions and on the sub-organic matter. And actually, the sub-organic matter should be related to the very structures of several particles of organic matters. And I would say the size of the pores. And the size of the pores is controlled by I would say the aromatic moieties and the size of the aromatic moieties. And it makes a lot of difference actually if the organic matter derived from lignin, from other type of alginite and stuff like that, you get some small pores with a lot of interactions between the hydrocarbons and the wall of the pore when you are dealing with, I would say, your type, I don't remember exactly, but say F, for instance. Okay? Yeah. And when you are looking at a system which is more leptinic, the size of the pore is bigger. And then the sorption is lower. So there might be a sort of possibility, perhaps, to reconcile the two approach, the chemical approach and your facies approach. Could you comment on that?
I think that's exactly the way to go. And I think, I was kind of dragged out of the lab in 1989 and told to go back and be a geologist again. And so a lot of the, the sort of very basic ideas that are in the models right now really haven't been refined in any way or in any validated in any real chemical sense, like you say. So I wonder whether that there is a need, I think, in the industry right now to be able to, especially in unconventionals, would be the sort of business reason to do it. So when we measure an oil saturation in a rock, typically the petrophysicist will do a Dean Stark extraction, which we know is not only excavating all of the molecules out of the pore network, but also the kerogen network, and it's also pulling apart the kerogen network itself. So I would have thought, it'd be very interesting to kind of see if we could motivate some kind of further research with that as the motivation, but also, conventional source rock behavior would benefit from the same thing. As how do we estimate the sorbed oil content? Because right now what's happening is that the petrophysicists don't have an alternative measurement. So what they're doing is they're taking this Dean Stark yield, which is also inflating the porosity of the rock, because you're creating porosity by pulling oil molecules out of the kerogen that is being measured by the helium porosity, and then you're reporting it as a saturation. So you're exaggerating the porosity, and you're exaggerating the real fluid oil saturation in that porosity because you're counting sorbed oil. I would have thought that there's enough money riding on that, literally, in the $1 trillion that have been spent on US unconventionals. But they're probably, you know, you could argue maybe there should be some enthusiasm in the industry for trying to sort that out now. So I totally agree with you, and I think there's lots of practical applications in addition to the ones that when we originally started out worrying about this stuff.
Yeah, okay. Yeah, I think the point is actually for the unconventional, because it becomes crucial for unconventional, this problem of sorptions.
Yes.
And relation between sorptions and types of organic matters.
Yes, exactly. Yeah. So as I say, I only stopped work on that because somebody forced me to, you know. So dragged me out of the lab. So anyway, so now's my chance to get back to the unfinished business a little bit.
Okay, thank you.
Okay, anybody else?
Any other comments? Yeah.
Hi, David.
Yes.
Hey, this is Xiong.
Hi, Xiong.
Can I show you guys one page of a paper, please?
Yeah, sure. Hold on.
You guys see this page?
I made you a presenter. Now I see the slide, yes.
Yes. Okay, this is a paper by Peterson.
Let's close the cameras so that we see the paper. Andy, can
I don't have a camera, so
I know.
probably don't want to see me either. So
Andy Pepper, can you please turn off your camera for a moment and we can maximize the screen?
Okay.
I don't know if you can read the letters, the numbers.
I can.
All right, so you can see that the last column here is HI.
Mm-hmm.
Then they go from 100 something to 700 something. Right? Guess what these things are?
Well.
Look at the second column.
No.
Coals.
Second column, TOC. Okay, it looks like coal. Yeah.
So given what Andy has talked about, and this is a piece of good evidence for classification by looking at HIs.
Yeah, so you can get anything
or not so.
From pure gas to a lot of oil out of these samples.
Right. I've seen other coals that have 600, 700 HIs as well. This is from Greenland, though.
What age are they, Xiong?
Oh gosh, I'm sorry.
Jurassic.
What's the title say?
The Middle Jurassic.
Middle Jurassic.
Oh yeah. Okay.
The Middle Jurassic.
Interesting.
Yeah. As for Wayne's comment about having looking at incorporating TLC into the Van Crevelen diagram, right? I think Andy had a slide where it's with the big bubbles.
Yes.
Right. So that would be a way of weighing things. Yes, I agree totally that a lot of times you just have 50 points along the type 3 axis, right? And there's 1 point up on their type 1, right? But that 1 point generates 10 times of hydrocarbons than all 50 of the type 3 samples combined. right?
Yes.
And if you talk about, if you actually consider expulsion, then all those 50 may not expel anything because it's all adsorbed or be residual saturation in source rock.
Yeah.
Yeah. So,
And you know, given that we were trying to hit a sort of a half an hour period today, what I didn't get a chance to go into was the kind of UEP logging approach, Xiong, that obviously is the solution to that. You know, maybe that's a talk for another day. I'm not trying to volunteer you or anything, but talk for another day on the importance of that, and as well as worrying about your HIs, worrying about what is the net thickness of each of the components in this table of HI that you're going to put into the model. So and again, it just comes down to describing your source rock in every dimension. So where are the ITOC streaks? How representative are they? All that kind of good stuff, which is, I think, where you're going. That's a cool paper. I don't remember seeing that one.
Andrew Murray forwarded this over to me. I think it's relatively new. No, it's actually 2002 here. APG.
Okay. Right.
It doesn't seem to have a high, oxygen index column, so I'm not sure if we can plot this on the background line.
Right.
Yeah, I'll use back to you, David.
Yeah. Okay. Yes. Thanks.
My screen.
And anybody else?
Did Alan have something that he wanted to put up there? I don't know how much more time we have.
I think it's pretty much open, as long as people stay around and there is an energy, we can stay up. It doesn't matter to me. Yeah. No, it would be. Yeah. Go ahead.
Andrew Green from IGI. I'm just wondering. Obviously, you mentioned the importance of measuring the gas versus oil behavior of the samples, i.e., producing this Gogi figure. I presume the only way of doing that is through conducting a pyrolysis GC. Is that correct, or is there other ways of measuring it on mass numbers of samples, kind of economically?
I do believe PyGC is the way to do that. That's certainly the way that it was done at Sunbury. And I think there are two. There's one word of caution I would say there is that there are two ways of integrating a PyGC yield, and I've seen some results on, for example, the Bakken, where people only integrate the resolved peaks, and it makes the Bakken look like the gaseous source rock in the world if you do that, because there's a lot of unresolved branch cyclic and aromatic material that's under the hump on the GC that is part of the yield. And so typically the kind of numbers that the BP lab would generate by doing the baseline integration, including the hump, would be, for a high quality 500, 600, 700 source rock, your Gogi would typically be about 0.15 to 0.2. That's a gas divided by oil ratio in mass terms. And then as you go further up, the organophases F are sort of interesting, and you get into a little bit of a, sometimes pyrolysis doesn't do a very good job with coals, and I think sometimes what it does is it smashes up the framework of a coal rather than actually generating it in the sense that it would be generated under a slower heating rate. And so what that can sometimes do is it gives you this flush of aromatic hydrocarbons from smashing up what in nature really is the aromatic network of the coal. and sometimes then you can see that sometimes the machines will report low gogies and high hydrogen indices because there's a bunch of aromatics coming in that aren't really generated in nature. So I think whenever I see coal data with high HIs, and in the absence of looking at a pyrogram, I must admit there's always a little guy on my shoulder that says, are we sure this is not the smashing up of the inert kerogen that's going on? So that would be my only caveat there. So we did see in the BP system sometimes some coals would generate high hydrogen indices and very low gogies, and you looked at the pyrograms and it was all aromatics, and you know that when you extract a coal, yeah, there's aromatics are generated, but not in that kind of quantity. So that's just a little caveat there. But yeah, to come back to your question, is the pyrolysis GC, and I guess it's just the way I was brought up was that you would always look at the pi GC of every sample that was more than 2 kilograms per ton, and the industry for I don't know, reasons of cost or whatever it is, the rest of the industry never kind of bought onto that. So there are a lot of folks like Horsfield and Dembicki done great work on fingerprinting the organic type from pyrolysis GC, but the idea of using it as a gas-oil split seems to have been something that somebody taught me at BP, and I've not really seen it widely used elsewhere.
Perfect, thank you. I mean, we're trying to do the same now with the digital data. I mean, getting back to the pyrolysis machine and looking at the pyrograms rather than just taking the data. As you say, it is important to look at the traces. So, and that absolutely easy to kind of pass around and store. It's definitely something we should be promoting, definitely. So yeah,
absolutely, yeah. Is there a lab that do you guys do? I'm not sure what you do.
No, we do the interpretation side and the modelling using D2Ed software. So we have, I suppose, a number of commonly used labs that we kind of push samples to, but we're not tied to anyone in particular. So if a client's got preference or wants something specific doing, then we'll find a lab appropriate for the analysis.
Yeah. Would you find that a hard sell to tell a client that, well, actually, there's we really should be measuring this extra thing? Would that be difficult for you, think? And well, everything's difficult in this environment, but
nowadays, but I mean, we have, particularly from the unconventional side of things, we've kind of found need to go back and, like, for example, reanalyze extracted samples back on a pyrolysis on a rock Eval machine to see the difference of removing the S1 and rebalancing as per Jarvi suggested. So I think if there's a good reason and there's examples of it previously, then companies are willing to invest the money, definitely.
Yeah, I mean, what Kinetics will do? Oh, sorry.
Go on. It's fine.
So what Kinetics will do for you, that in recognition that the rest of the world wasn't going to be like the BP lab data set, we actually put some default correlations in there where, broadly speaking, HI and GOGI are inversely correlated. As Andrew Murray has pointed out, I think, and other folks that have worked in the Northwest Shelf, where there's lots of public data, that is not the world's most impressive correlation, mainly because there isn't, strictly speaking, a link between HI and GOGI. But there's a sort of a general one. So the numbers that are auto suggested by Kinetics are based on a cross correlation of, I think there's probably like 1,000 samples or something of the different organophases. So that'll get you by, but surely we want to measure gas oil ratio. If you want to know gas oil ratio, then we should just measure it. So that's the idea anyway.
Perfect. Thank you very much.
David, can I make a comment?
Yeah, sure.
I'll just turn the camera on so people can see. Oh, that's a terrible sight.
So this is your 10 minutes that you wanted to stay for.
Yeah.
Hey, how you doing?
How you going? My phone credit's going to be maxed out, but there you go. It's worthwhile activity. Firstly, Andy, thanks for offering to do this. It's brilliant. Everybody appreciates it. It's a great opportunity to listen to you speak about this topic. So thanks for that. The other thing I'll say is that right now is that I've said it to you private, and I'll say it in public, that what you and Peter Corvey did, I think, was a great service to the industry, and it's made an enormous difference, I think, to the way that we go about our business. So thanks for that. You just during your talk, you made a few comments I think were aimed at discouraging people from turning your kerogen type description into types. In other words, don't overinterpret them as types. What I'd say about that is that humans are inveterate classifiers. They will do that anyway. They've done it for years with type 1, type 2, type 3. And I think moving to A, B, C, D, F is a big improvement. So I would just accept that's going to happen if I were you. And I think it's a great step. If everybody was speaking about A, B, C, D, and F in the way that they speak about type 1, 2, type 3, I think that would be a big step forward. The only other thing that I probably wanted to mention was that the system is a two-phase system. We speak about oil and gas, and we're talking about gas, C1 to C5, molecules C6 plus for oil. And that's fine, that's a good starting point, and I think that's how we calibrate our systems. But I think it sometimes gets forgotten that when we speak of oil, we're really speaking about liquids. And in that classification, we have something which will manifest in a petroleum system as a gas condensate, and something else which will manifest as an oil depending on the boiling range. Now, if we all had GOGI data, we would also all have PyGC data. And therefore, we'd have the ability to tell which source rocks are generating mainly C5 to C15, and how many are generating C15 plus. And then we will be able to model, I think, predominantly gas condensate systems a lot more effectively. And in Australia, we have a lot of gas condensate. So if you had any inroads into BP still these days, I'm not sure whether you do, but if you could encourage them to find their gas pyrolysis GC database, because I think it probably still outstrips any PyGC database in the world, and release the data so that the rest of us could split it up into condensate and oil, I think that would be a great thing to happen. So I just wanted to see what you think.
That's a good point, because actually, as well as the gas, as the C1 to 5 versus C6 plus split, there was a split every 5 carbons through the rest of the distribution, and just it sort of resonating from what you said there. There was a C, what would it be? The C25 plus was given a parameter called WOGU, so the wax oil generation index, and as you probably know, that's when you have these coals that are on the limit of whether it's sorbed or not, whether you can reach the sorption threshold, it helps. I think physically what's happening is that the longer the chain that you're trying to crack, the more chance you have of the compound you generate still being in the oil range, in the lighter oil range. So yes, so those data were all done. I don't know if there's anybody from BP on the call right now. Certainly, I could follow up with my former colleagues there and see whether that's possible.
Yeah, that'd be brilliant.